In the last part of the program, we saw how to replace a fuse in a fused cutout switch and how to safely replace the cutout itself. In this portion of the program, we'll see how various types of reclosers are designed and how they operate. We'll also examine a typical operating cycle. Let's begin by looking at a simplified drawing of a single-phase recloser so that its basic parts can be identified. This recloser has a tank with two bushings located on its top. In a cutaway, the conductors running through the bushings into the tank can be seen. Each conductor ends at a contact. The tank also contains the operating parts of the recloser. This recloser has an internal control mechanism which is made up of two basic parts, a control unit and a series trip solenoid. The solenoid is attached to a plunger. The plunger is moved up and down by the solenoid and is used to open and close the circuit. When the plunger is in its down position, the circuit through the recloser is closed. This type of control mechanism can be classified as electromechanical. Let's see how it works. When current flowing through the circuit in the recloser is greater than the value that it has been set for, the solenoid opens the connection. After a set period of time, the control unit closes the contacts back in. If the current is still too high, the solenoid opens the contacts again. The control unit counts the number of times the recloser opens in a cycle and times each operation. Some reclosers, like this one, have control units that are located within the tank. They operate mechanically, for instance by pumping oil through separate hydraulic chambers or ducts. Other reclosers may have a solid-state electronic control unit, which is located in a separate box lower on the pole. The control unit is connected to the solenoid in the recloser tank by a control cable. This type of recloser can be opened or closed manually from this box by opening a control lever. The electromechanical recloser in this drawing can also be operated manually, with a control lever mounted in a housing on the outside of the tank. When the solenoid operates to open the contacts, an arc can form, so the recloser tank contains an arc-suppressing medium, such as a vacuum, SF6 gas, or oil. The type of control mechanism and arc-suppressing medium used are two of the ways that reclosers can be classified. Reclosers can also be classified by their capacity. The load that a recloser is able to respond to is a measure of its capacity. An increase in load demand in an area may require that a particular recloser be replaced with a unit set at a higher capacity. Reclosers can also be single-phase or three-phase. Single-phase reclosers are commonly used to protect single-phase lines, such as lateral circuits and branch circuits. Separate single-phase reclosers are also used on each phase of some three-phase circuits, such as those in residential areas where the load is predominantly single-phase. In this diagram of a three-phase feeder, a single-phase recloser has been installed on each phase. When a fault develops, the recloser on the affected phase begins to cycle and will eventually lock out if the fault does not clear. The other two phases are unaffected. Three-phase reclosers are used where lockout of all three phases is needed on a permanent fault. For example, this type of lockout prevents single phasing of three-phase loads such as large three-phase motors. Three-phase reclosers will generally have one of two modes of operation. One is single-phase trip and three-phase lockout, and the second is a three-phase trip and three-phase lockout. We'll use the diagram of the feeder to see how each type of three-phase recloser operates. For single-phase trip and three-phase lockout, three single-phase reclosers are contained in a single tank with mechanical interconnections for lockout. When a fault occurs on one phase, the recloser mechanism for that phase operates separately for overcurrent tripping and reclosing. However, if the fault is sustained and the phase locks out, the mechanical linkage trips open the other two phases and locks them out as well. For three-phase trip and three-phase lockout, the mechanisms for all three phases are mechanically linked. They operate together for each operation of the recloser. This means that a fault on any one of the phases will cause all three phases to open, close, and lock out at the same time. Regardless of how a recloser is constructed, they're designed to respond to an overcurrent by cycling through a series of openings and closings. The cycling continues until either the overcurrent disappears or the recloser locks out, isolating a section of the circuit. Variables such as load demand, size of the area served, type of equipment being protected, and climate may affect the timings used. Each recloser in a distribution system may have to be set differently. We'll use this graph to see what happens during a typical cycle and compare it to the simplified feeder circuit below. The graph shows a cycle of 4 operations or closings. The 2 closings on the left are short to attempt to clear a temporary overcurrent. The 2 on the right are longer to allow cutouts time to operate. The flat lines in between each closing indicate that the recloser is open. The times shown here are typical. Notice that the length of time that the recloser is open increases with each operation to allow heat-sensitive equipment time to cool. Cooling avoids premature operation of fuses. Let's follow a recloser through a typical cycle to lockout. This line shows the circuit operating normally. The overcurrent begins here. The recloser opens and then closes again almost immediately for its first short operation. The overcurrent is still present, so the recloser opens again and stays open for 15 seconds. Then the recloser closes in its second short operation. The recloser still senses the overcurrent, so it opens once again, this time for 30 seconds. The next time the recloser closes, it closes long enough so that any cutouts in line will sense the overcurrents and operate. Then, the recloser opens for 45 seconds. The recloser closes one more time. If an overcurrent is sensed, the recloser opens again and locks out. Once locked out, the recloser must be reset and closed manually. If the overcurrent had disappeared at any point when the recloser was closed, for instance during the second short closing, the recloser would have reset to the beginning of its cycle and the circuit would remain energized. Keep in mind that this recloser cycle is presented only as an example. The timings of each recloser in a distribution system may have to be figured separately.